Welcome back. In this episode, we take manufacturing to the next level with 3 powerful multi-blocks, the engraving laser, circuit assembler, and cutting saw, boosting our circuit efficiency like never before. This is Star Technology. Let's get into it. So I've been getting a few comments on my videos lately asking why the quest log looks so different to what they're seeing when they load the mod. If you install Star Technology right now as of this minute, you'll get this version, which is 1.20. It is the latest version. It is being actively maintained. So the version that I'm running this playthrough on is 1.19, which is slightly different, but most notably in the quest log. This is the quest log set up for in the 1.20 version. Under progression, you've got like early game, industrial revolution, automation age, which is quite different to the layout you would have seen in the rest of my videos where it's, LV, MV, HV. It's all based on the technology tier. So even though the quest tree is arranged differently, the same technology exists underneath the hood. They've just grouped it more logically rather than by the technology tiers. So you can see that particularly with, this is all the early game stuff, and some of these things, like this basic electronic circuit in the 1.19 version appears on the LV page. The things you need to kind of work towards this are all here. It kind of makes more sense, like this should be the final thing that you're aiming for on this page. And the same applies like in the Industrial Revolution page, like you're working through and you get to these printed circuits, you're starting to get to your applied energistics. The keystone ones, like the bigger ones, kind of give you what you should be working towards. I just wanted to kind of point that out because if you are playing along and you're looking at the quest log that I'm showing on the screen, it's going to be different. And so you might be a bit confused. But aside from bug fixes and a few tweaks to a few mods, it's the same game. The 1.20 quest log is much better. Like it's laid out a lot more logically. It would have been nice if I had started on 1.20, but the fact is it wasn't out when I started the playthrough. So yeah, there's that. So since the last episode, I've spent a bit of time just collecting some of these items that we needed for these quests. Some of them were pretty annoying, like this glycerol and hypochlorous acid, because we didn't actually use that in our process to make the liquid epoxy. I've grabbed those, ticked them off. I've also built a bunch of these epoxy printed circuit boards, encoded the new circuits and built a bunch of them, and ticked off a lot of things. So that's all good to go. I've also gone ahead and created all these different alloys along here and actually grabbed a few of the ingots so I can tick them all off. So let's clear the quest log now. Look at that. Lovely. So how many did we get? 26 Star T coins. Is there anything we can actually spend these on at this point? This is the shop. I mean, really, there's nothing, isn't there? Yeah, it's kind of lost its appeal since we got past the flux networks, really, isn't it? Because this is stainless steel. This is like, many tiers behind where we are now. And speaking of which, we are really close to having LUV. I realized because of the polyvinyl butyrol that we had to create, I can tick off a few things there. So that's all been done. So we've officially made progress into LUV. So the two main materials that we need for frames and for wiring in LUV are the rhodium-plated palladium ingots and the twinite ingots. So I've made a bunch of that, made some wires, and so we're pretty much poised to start building some of these. Now, there is something stopping us with this LUV machine hull. We're missing something called polyphenylene sulfide. I'm not ready to do that right this second, but we will do that this episode because what I want to do first, it's probably time to start building the large engraving laser. So what does that look like? The large engraving laser is a multi-block. It's a decent sized one, 5x5x4 from the looks of it. And this needs to sit in the clean room. So we're going to have to move some things around. The good news is it's got lots and lots of spots free to put buses so that we'll basically replace all of the engraving lasers that we have. And in addition, there's a very cool trick you can do with it, which is this thing here. So something called a parallel control hatch. Now, as the name suggests, and the tooltip says, it can run up to 4 recipes in parallel. So the large engraving laser looks like this. Got IV emitters, IV circuits, an elite laser engraver in the middle there, some platinum cables, double tantalum carbide plates, electric pistons. It's not too difficult. Probably the most complicated part was the IV emitters, but we've been able to build those for a while now. It's not too difficult now, where we are at the moment. So it's got a lot of these laser-safe engraving casings, which look like this. Titanium tungsten carbide plates, titanium frame, program circuit 6, It's very similar to all the other things we make. requires a tungsten steel pipe casing, some assembly line gratings. They're not too hard. They're pretty low tech. They're iron bars, steel frames, MV electric motors, and that fan there, which isn't showing up for some reason. So what I'll do is I'll grab these components and then come back, and then we will build one of these things. All right, so I've got all the parts for this, but I guess first things first, I need to make a space in the clean room for this to actually work. Because we're replacing all of these laser engravers here, I guess we'll just take up this space. So it's going to come right out to here, unfortunately, but I mean, that's just how it goes, I guess. So I'm going to have to get rid of all these and collect all these different lenses because we're going to need a bus for each of these. Got to clean this up, so I'll do that and come back. It's probably time to start building. So we'll start with the energy hatches. So I'll actually put them over here, like that. And then I'll hook them up already just to make it easier. So the controller goes here. It's a pretty big machine. And then we'll just fill in the base. Tempered glass up the sides in the middle, like this. Then sort of like a structure around like this. This is tungsten steel pipe casing that kind of has to hang off the side somewhere. So let's put some scaffolding here. That pipe casing like that. Then we need the assembly line gratings around like this. Auto maintenance hatch, which I guess I'll just put down here. Is that it? That's it. Cool. All right. It's quite an unusual block, but it should be powered up. It's running on LUV power. Now we're going to need loads of inputs. So we're going to need at least 7 for each of these diamond lenses and the different pattern providers and things. So we're probably going to end up using all of these top face blocks here. That would probably be the easiest way to do it, wouldn't it? I've gone through and created separate buses for each of these and loaded them up and put pattern providers on each of them, and then also remembered to turn on distinct buses for each of them because I'm pretty sure that would be a problem otherwise, because it seems to just try and share them and would make the wrong recipe. So let's see if we can do this SOC wafer. There we go. It worked. Okay, let's try one of the others. Let's try, what's in this one? The CPU wafer. Let's try making some of those. Just to make sure that it is working. Oh, nice. That's quite a lot quicker than the machine was before. Now then, all right. What about the parallel control hatch? So this allegedly allows us to run up to 4 recipes in parallel. So how does that actually work is a great question. So let's put this in here. Now that's in place. Now this is, I guess, how many we want to run in parallel. So we'll go to the max. So in theory, if we request, say, one of those SOCs, that's taking 6 seconds. Right. So if we request 4, that's now taking 11 seconds. But it made all 4. Okay. So that's not quite how I thought it was going to work, but that was quicker. So SOC wafer, the recipe for that is HV. Normally takes 45 seconds, so it's overclocked to LUV. It should be 0.7 of a second, but it wasn't, was it? Why was that 6 seconds? So, okay, what that means is it mustn't be a perfect overclock, so I've done that wrong. So if I go through, like, okay, cool. So it's not 6 seconds, it's 5.6 seconds. Running 4 recipes together, for some reason, took 11.2 seconds, I'm guessing. It's not 4 times faster, it's twice as fast. A little bit odd. That's not how I would have thought it would work. Well, I mean, it's faster. The rule, I don't fully understand the rules of how it works, but this is a pretty good thing to have. There's other parallel control hatches as well, so we will be able to upgrade that. To start with, we get 4 recipes in parallel, then later on we can get 16, but we won't have that for a while because it requires an LUV emitter and ZPM circuits. So we'll be getting that a little bit later. But that's pretty cool. So for the SOC wafer, from one phosphorus doped wafer, it produces one SOC. I wonder if I should re-encode this pattern to be 4 at a time, because then it will always take advantage of the parallel. All right, let's just change that. So I should be able to do that with my cool little remote terminal here. So if I change that to 4 and that to 4, drop that in there. If I ask it for just 1, well, looks like it has, yeah, because 11 seconds. So what I might do then is just make sure that each of these has been encoded so it's producing at least 4 at a time. Well, yeah, 4 times the quantity, and that way it will take advantage of that parallelism, I guess, every time. And I guess the next step would be to do the same thing for the circuit assembling, because there's a large circuit assembling facility. That's what that block looks like. It's a weird shape. We'll have to nestle it into that corner behind the screen there. It's very similar kind of equipment. There's the assembly line gratings. There's something called what's that? Large scale assembler casing, some glass, and we can parallelize that as well. So that might be worth doing. We'll get rid of all these different machines. I've gathered all the components to make the large circuit assembling facility. So this is what the multi-block looks like. A load of these assembly line gratings. It's got some tempered glass. It's got the controller block itself, all the usual hatches and things. So there's nothing too scary in there. Tungsten steel pipe casings inside as well. Spent a little bit of time just shifting these over, which gives us just enough room to squeeze it in here. It's a pretty big block. So we'll see how we go. I think in the future we'll probably remove these. Yeah, so I guess what remains now is just to dismantle these. So I'll get to that. Get rid of this EV energy converter and that flux point. So start with the energy hatches. And if I use the wrench, I can rotate them into place. And so I need 1, 2, 3, 4, 5. Geez, this is a big block, isn't it? Okay, then we need the multi-block there, I noticed. Auto maintenance hatch. Let's do that. And the glass was 1, 2, 3, 4. And then do a bit of this. And then we just go like this. Can't tell if that's worked. No, it doesn't. What are we missing? I don't know if the orientation of that matters, because on the multi-block it's facing this way instead. Okay, well, after a little bit of fiddling around, I got it to work. As it turns out, the orientation of the actual controller block matters. So if it's facing this way, everything's happy. If I take this out and point it this way, it doesn't complete the multi-block. So that was a surprise. I didn't realize that. I guess because all the multi-blocks we've made up until this point, you know, the controller block has been on the front, so you couldn't really have a different angle on it. But that's okay. We'll work with that. So we can put it like that, and that's happy. Now the other thing is, I was expecting to be able to overclock this. So I made space here, I put in a second IV energy hatch, and it doesn't work. So it can't be overclocked. And I had to think about it, because it didn't really make sense to me, because this one we just built here, we did overclock, because this is LUV now. The reason why, I believe, is so you can't skip ahead with circuit tiers. If you could overclock this, you'd be able to do LUV circuit making recipes in here, which would, I think, break the game a bit. So they've made it so the only thing you can do is put like a 4 amp energy hatch here. So that's what I'll actually do for speed. So this doesn't overclock the recipe tier, it overclocks the speed instead. The recipe tier is still IV, but it's actually running at LUV speed. That's actually what I want. I want it to be faster. So yeah, okay, that's a lesson learned. I guess that's artificially limited on this block because it would kind of break the game if you could skip ahead, I think. So I need to add all of these recipes in, put some input and output hatches. So let's do that. Let's put this here. That can come just straight out there. type of recipes we're going to be running in here actually require liquids as well. So probably just do it here actually. Let's keep it compact. MV input hatch, MV input bus. So that should take quite a few different materials. And now we just need an ingredient buffer. So put that on there, pattern providers, and grab these guys. There we go. Then we just need a pipe to go into that. So we use pipes mod. Seems to work quite well for me. So put that on there like that. Do that. Put that in there so it's quicker. Interface. And then we should just be able to hook this up. Like that. So in theory, we should be able to request a circuit. What should we make first? Let's make one of those really big ones that take a long time. This is an LUV tier circuit, so should be fun. There we go. Ooh, that's fast. Well, I mean, it's definitely working. Cool. All right. Well, that was pretty quick. So now what we need to do is probably just change that recipe so it forces it to bulk craft. Just multiply these out, I guess. I mean, it seems like it's faster. It's got a parallel control hatch on it. It should be doing 4 at a time. So that's another thing we've ticked off. So this should allow us to make circuits much quicker. The only thing we have left in the chain is this cutter. So there is actually a multi-block cutter, but I don't know if it's going to fit in that little space there. The clean room is getting a little bit cramped. So the large cutting saw looks like this. It is just a bit too big. I think the cutting operation does require the clean room for these. Let's have a look at an example. Nano CPU chip. No. Okay, that doesn't require a clean room. Do the recipes in here even require a clean room? Okay, let's go HPIC. That doesn't require a clean room. Maybe these don't require a clean room. Maybe I just put it here because it was just convenient. Well, you know what? I don't think this needs to be in here. So I can build a cutter out there somewhere. And that'll take care of that. Okay, that's very cool. I'll get to that. So I figured it out. When you cut the phosphorus-doped monocrystalline silicon ball into the phosphorus-doped wafers, you need a clean room. I put that in here, and then at some point, I started adding all these other recipes. So none of these need to be in here. It's only this one. So that means, I mean, I could leave this here, and the rest could be in a cutter that's outside the room. So I might do that, because I think it'll be a lot quicker. So the large cutting saw is not that hard to make. Just involves tungsten carbide buzzsaw blades, IV conveyor modules, an elite cutter, an elite lathe, some circuits, and some motors. There's also these slicing blades, which are made from tungsten carbide plates, ultimate gears, shockproof cutting casings, and IV electric motors. And then the shockproof cutting casings themselves are just basically Hastelloy. We've seen this sort of shape before a lot, so it's nothing new to us. So prep the area, put in the wiring that's needed. Let's get to it. Rotate those into place. Now this is a pretty large multi-block. It's 7 by 4. So I guess let's just lay that out. The controller block goes here. And then I'm pretty sure this just kind of goes around like this. There is actually a cavity there. There's also all these slicing blades. So these go here. There's a bit of glass at the front. And then I think it's just a matter of just going around and making sure we just leave a gap there. Now I think that's filled in like that. And then I think we just fill over the top. It actually uses a lot of these blocks. Should have enough. We still need to place the auto maintenance hatch. Actually, no, we'll put it here and then we'll put the parallel control hatch in that other spot. And there we go. Should be working. Let's grab those recipes from over here. It's getting a bit cramped in here now, isn't it? This one here is the one that does require the clean room. I'm pretty sure all the rest do not. So I guess we'll see. So let's start with these chips. Let's go MV input bus, MV output bus. input, output, pattern provider. We'll load all these in. And then interface to pull out the products. And then we just need to cable this up. So the machine has two different modes. It can be a cutter or it can be a lathe. So for this purpose, I'm going to use it as a cutter. Ah, hang on. We need lubricant. Because this is always going to use lubricant, maybe I'll hook up a bus so that it's just always stocked. But we do need an input hatch, so I'll put that there. And just say this is going to be lubricant. Coming in pretty slow, but this machine won't be using it very quickly, I don't think so. Now, what I need to do is change those recipes. So let's do the NOR memory chip just quickly, just to prove that it does work. So I can do it from this terminal here, which is kind of handy. If I take that out and then pop it back in here. Oh, there we go. Yep. That's pretty quick. Yeah, what I've got to do is go around and just fix this up. Probably multiply each of these by 4 as well. I'll do that and come back. I've re-encoded those recipes and also brought in the other ones. And this is blisteringly fast now, which is amazing. So the slowest part of this whole process is just basically this chemical reactor, I think, that's left in here. That makes these nano CPU wafers, which is pretty slow. And it has to be in a clean room, unfortunately. We'll have to figure out a solution to that. I mean, we could put it into here, I guess, but this is set up to passive these HPIC wafers. But yeah, we'll probably just reorganize some stuff. But that is pretty cool. So now I have 3 of these new large block machines that we've managed to put parallel control hatches on. Let's tick those off. That would be that one. And that one. And that one. Now, I did have a play around with the large centrifugal unit. So this replaces the centrifuge. It's an interesting multi-block. It looks like this. Very like a spinning kind of disc thing in there. You can put a parallel control hatch on it. But as it turns out, it's actually slower than the centrifuge we already have. If I come over here, this is the centrifuge I replaced, and I've since put it back. So this one is set to be processing my stone dust, and it's just sitting there churning away. It's, you know, less than 1 tick apparently per cycle, which is what it needs to be because we have so much stone dust. But I replaced this with one of those large centrifugal units, and it was slower, even using the parallel control hatch. It was taking about 3 seconds per cycle instead of less than 1 tick. And then I realized what it was. It's because this machine can do perfect overclocking. Stone dust in a centrifuge is an MV recipe, so if you perfect overclock that to LUV, it takes 0.05 seconds, which is what we're seeing in front of us here. If you use the large centrifugal unit, what happens is it doesn't perfect overclock. So if I take that up to, say, LUV, now it's taking 1.5 seconds. It seems like the machines that can perfect overclock, you're better off using the large machines. So it would be, you know, the centrifuge, the electrolyzer, probably the chemical reactors. They work slightly differently. Yeah, notably, the 3 machines that I've built so far, the cutter, the laser engraver, and the circuit assembler, they're all machines that this is the first multi-block that we've had. We haven't replaced it. So what that means is a lot of these machines along here we won't bother building, which is a bit sad because some of them look pretty cool. So for example, the large wire factory, I'm not going to build that because I'm pretty sure that the one we have is already running as fast as we can go. Maybe okay, so the electromagnet's probably worth getting because we don't have a large block version of that. So we'll probably do that. And then, yeah, if we wanted to have brewing or using the arc smelter a lot, then we'll probably do that. But yeah, for a lot of these, like the mixer doesn't seem to be worth it. Material press, the maceration tower, definitely not, because we've got macerators that are really fast. So yeah, bit of a shame. But that's all right. I mean, we just probably grab those few there that I mentioned. The crystallization chamber, which I think is an autoclave, that would be amazing. So yeah, we'll build a few more machines, but not all of them, as it turns out. So some of these alloys are a bit of a waste because you'll probably never use them. And so where does that leave us in LUV? Probably the energy converter, right? What's involved with that? So 16 times twinite or twinite? I have to make a decision. What am I going to call it? Twinite? Yeah, twinite. Okay. 16 times twinite wire, LUV machine hull. I think we can probably make that already. I think I encoded it. Can we build that? No. Oh, okay, that's right, because we need to make that polyphenylene sulfide sheet. So I guess that's the next step. It's actually not too hard. It's only 3 steps. Basically, you start off by making something called sodium sulfide. Sodium sulfide is dead simple. Sodium and sulfur reacted in a chemical reactor. So the other thing we're going to need is dichlorobenzene. Now that's created by reacting chlorine and benzene in a chemical reactor. Not to be confused with chlorobenzene, which is a different chemical entirely. We use that in our process over here. The same ingredients, different program circuit. And then once you have those two, so sodium sulfide and dichlorobenzene, we react them together to make liquid polyphenylene sulfide and a byproduct of salt. So 3 chemical reactors will take care of this. So let's get to it. So fortunately, we don't need to mess around with large chemical reactors for this process. We can just use regular elite ones. So I'll actually just place them in right now, I guess. Make sure they're all getting power. Cool. So the first thing we're going to make is the sodium sulfide. That requires sodium dust and sulfur dust. Now, because we're dealing with solids here, we're going to need to use some sort of robotic arm and a filter just to make sure that we have the right quantities. So let's get that happening. So put the robot arm in. Let's put the item filter on that. Tell it to import, keep exact, and then we'll drag in the sulfur and sodium dusts. Let's increase these up to, say, 16 each. What we need is an interface on here, and we'll import those 2 things. So sulfur and sodium. There we go. Silence that. Now the sodium sulfide can go straight into this machine here. So let's just tell it to export, like that. So all we need to do now is create the dichlorobenzene. So we'll do that in here. First of all, program circuit 2, because we don't want to create the wrong thing. So dichlorobenzene is made program circuit 2, chlorine and benzene. So let's put an export bus on that, add a capacity card, and then tell it to import the chlorine and the benzene. Put some accelerators in there as well. There we go, dichlorobenzene. So we're going to want to get rid of that hydrochloric acid. So we can do that with an import bus. Let's tell it to import the hydrochloric acid. And then we can put a storage bus here and then partition it, but then remove the hydrochloric acid. So this is only going to be a source of dichlorobenzene. Now in here, all we need is oxygen and dichlorobenzene. So we can put an interface on here and tell it to import those 2. We need the dichlorobenzene and then we need oxygen. Now that those 2 chemicals are coming into the interface, we're going to need a pump to import them into the machine. Tell that to import. There you go. And so now it's making liquid polyphenylene sulfide. Now it has a side product of salt. So what we can do is actually push that into the interface to get rid of it. We do that. So that's now getting rid of that. But the liquid polyphenylene sulfide will be staying in there. And all we have to do now is put a super tank on that. Just tell that to export the fluid. There we go. Now we want this to be controlled. So let's put a machine controller on the front of this and a level emitter. So how much of that polyphenylene sulfide do we want? Drag that in there. Let's say 500 buckets maybe. That should be pretty good. And then we'll just extend this out like that. Right, I think we're done. Except for one thing, we need a storage bus on here. Otherwise we can't access it. There we go. So now we just need to encode a recipe to create the ingots and then those sheets. And I think we should be able to create our first LUV machine hull. So let's do that. So first of all, we're going to need to create this. So we can do that from an ingot. Do that. Encode that. And then we just need to do this. Don't need that. And there. And so now that means the LUV machine hull should be craftable. Done. All right, cool. We have access to LUV machine hulls now. Yeah, we've made a sizable foothold in LUV now. So I think we have that source of Naquader. Why don't we take advantage of this? So that'll be the next step, I think. Get this Naquader doped monocrystalline silicone balls. But I think that's something we'll tackle in the next episode. Well, that's a good place to wrap this episode up, I think. We got through quite a lot of cool stuff. Like, it's really upgraded our circuit assembling capabilities now. So we've got the cutter, the laser engraver, and the circuit assembler itself. So we can make circuits much, much quicker than we could before. I might actually build a few more of those multi-blocks, because there's a few that I think would be handy to have, like the assembler, for example. But we'll come to that next episode. Thanks for watching. Take care of yourselves and each other, and I'll see you in the next episode. Cheers.